this is your last content before the test. I think that this is very cool, and here's why. If I ask you what the square root of 2 is, what would you say? 1.41. Now, 1.41 is an excellent estimation. However, how did you come up with 1.41? You remember it from having used it many times. Suppose you were trying to come up with it accurate to 6 decimal places. Other than guess and check, what would you do? Okay, so Ashwin plugs in her calculator, and here's the interesting thing. She takes square root of 2 and she comes up with a number. Now, in your mind, maybe the calculator just has stored in memory what the square root of 2 is. Well, at the same time, you can take square root of 2.01 and you get a slightly different number. My point is this. Your calculator doesn't just memorize all the square roots. There's a process used. It's not the same as what we're doing today, but I will say Newton's method is an awesome, awesome way to find very, very close values to square roots. Yes. So his work was published very quickly. Math duels were kind of over by this time. The printing press came around, and a lot of stuff was then open for people to see. So your problem statement. This is our problem. This is the problem that Newton was faced with. He didn't have a calculator. In fact, if you talk to some of the older staff here, they may remember the first kind of calculator that they ever had growing up that would do just addition, subtraction, multiplication, division. Okay, and they were very expensive. When I was growing up, yes, we had scientific calculators, and they weren't all that expensive, and they could perform all the operations. But you guys do understand that with more computations, more memory in your calculator is used for those. And so as the development of the silicon chip and everything else has really changed the way that our world operates and the number of processes that can be accomplished. So again, I ask you square root of 2, you shout out 1.41, but then I say, what's the solution to x to the third minus 5? And other than saying somewhere between 1 and 2, you really don't know what to say. So here's what Isaac Newton said. He said, suppose we wanted to accurately estimate the square root of 5 to 4 decimal places. How can we do that? How can we do it quickly and efficiently? And here's what he said. I'm going to look at the function f of x is x squared minus 5. Anybody know why he chose to look at that function if he's going to approximate the square root of 5? Because the x-intercept is going to be the square root of 5. Now, it's between what two integers? Square root of 5 is between 2 and 3. Okay? Because 2 squared is 4 and 3 squared is 9. So, see, looks at this graph. Okay. It's a parabola, shifted down 5 units. So, this is x squared minus 5. What he would do is he would make a guess. Now I'm going to make a guess that I know is not really all that close, but a guess nonetheless. And what he would do is he'd say, I'm going to guess 3. I know it's not close, but I'm going to guess 3. I know I'm going to be off by a ways. In fact, I'm going to be off by, if you plug in 3, what do you get? 3 squared is 9 minus 5 is, I'm going to be off by 4. I'm going to be off by 4 units. That much. That corresponds to a point on the graph. Yes, no? He said, here's what I'm going to do. I'm going to find out a way to get really close to that point. I'm going to take that point, and I'm going to draw a tangent line to it. And once I draw that tangent line, what part of that tangent line is really close to the solution? The x-intercept of the tangent line. Would everybody agree that the red point is a much better guess than the black point? So therefore, the red one will be our new guess. And he would just do it over and over again until he came to a result that he was happy with. That's the calculus. Very simple, isn't it? Very simple. The derivative had not been formally developed. So again, this is just one small way in which calculus is extremely useful. We're just applying it in a very small way right now, but hopefully you can appreciate the genius of Newton. Yes? Okay. So we're going to write the abstract part here where we get the formula. We're actually going to do the problem here so you can see the connection back and forth. Okay? So approximate square root of 5. Therefore, what we do, if you think of the problem, is we wrote a function. F of x is equal to x squared minus 5. That was the representative function for the square root of 5. There's others, you know, you could choose others, but that's the one that we like right now. Okay. Now that we have that, what we said is that we want to make a guess. And we use that guess in order to come up with a point on the graph. Yes, no? We use 3 to come up with that point and then write an equation for line tangent. So what I want to do is if I guess 3, I need to come up with a slope and I need to come up with a point on the line. Well, if you notice, the point on the line is going to be, the x value is 3. Very good. If the x value is 3, the y value, Katie? 4. That was the difference. That's how much we were off by. We want that number to be small, and then we won't be off by very much. Okay? So, how do we get the slope? The derivative. It's calculus, right? So we're going to take the derivative. So f prime of x is equal to 2x. So therefore, the slope will be 6. Because 2 times 3 is 6. We plug in 3 and we get 6. So let's go to the abstract. Our function we'll refer to as f of x. In reality, what was our guess? 3. We will call our guess x sub 0. Sub 0 because initial guess means after no time has passed by. Now, I know we're not talking about time, but this is from the very beginning, so 0. That's why they like to use it. If you don't like it, just ignore it, okay? So now what I need is a point on my line. Look at the point on the line that I created here. Tell me what will be the x value. X sub 0. How do you come up with the y value? F of x sub 0, thank you very much. How about the slope? Over there we got 6. How would you come up with the slope here? Thank you. F prime of x sub 0. So we pause. Are there any questions how I came up with any of that information thus far? Amber. You could pick 3. You could watch what happens. Excellent question. Suppose you pick 2. Watch what Newton's method says. Newton's method says pick 2 and you find a point on that curve. Now it's down there, right? Then you would draw a line tangent, right? And you would find that x-intercept. You're still going to end up close, and if that's your new guess, you're still going to arrive at that spot. There are good guesses and bad guesses. You want to guess relatively close, but the question is what is relatively? And we're going to talk about good guesses and bad guesses tomorrow. For just very short. It has to do with local mins and maxes of graphs and stuff. We'll talk. Yep. Instead of what? Because 3 is just this one problem. I'm going to derive a formula for us to use all the time over here, okay? All right. Now that we have a point and a point on the line, let's write an equation. Y minus y1 equals m times x minus x1. Y minus what? 4 equals m. X minus 3. Now, if this is the equation for my line, tell me, what part of the line am I trying to find? The x-intercept. The x-intercept occurs when y is equal to 0. So let's not put it in slope-intercept form. We'll just put 0 in for y. Negative 4 is equal to 6 times x minus 3. We want to solve for x. What would you do? Let's just divide the 6 off. So negative 2/3 is equal to x minus 3. Then what? Add the 3. So you get 3 minus 2/3 is equal to x. So x is 7/3. Now, I want to just show you how this is working out for us, because some people weren't very impressed by this, and I understand why. But we guessed 3. We knew 3 wasn't very close, right? 3 squared, we got 9. We want to come up with 5. Well, if you take 7/3 and you square that, whoop, sorry. That closer? Some people are still not happy with that. That's fine. We only did it once. Our new guess would then be 7/3. So instead of choosing 3, we do the same thing over and guess 7/3. Only we don't really want to go through all that work. We pause, go feed your brains. We'll be back in a little bit. Okay. Let's pick up where we left off. So 7/3, we squared it, we got 5.44. That was a lot closer than 3 squared, which is 9. What do we want to come up with when we square it? 5. We're going to take this, which is a concrete example, and we're going to write an abstract representation of it so we can come up with a formula. Because if 7/3 is our new guess, there's a way we can quickly move through that. So I'll show you how that works. It's really cool. Equation for a line. Slope and point on the line. As you look at the information I have up above, what is the point on the line? X sub 0 and f of x sub 0. And the slope? Looks like I didn't even have to write it. It's just sitting right there. Just forgot being gone for break. So now the equation for the line is y minus y1 is equal to m times x minus x1. Correct? Now, I'm going to skip a step here. Remember, what happened to this y right there? Plugged in 0 because we're looking for the x-intercept, so therefore y is equal to 0. So this will go away, and I'll have minus y1. So minus f of x sub 0 equals m f prime of x sub 0 times x minus x sub 0. I want to solve for that. What are we trying to solve for? X. So we'll divide that off. So divide by f prime of x sub 0. So negative f of x sub 0 over f prime of x sub 0 is equal to x. I'll get rid of the parentheses since it's by itself. X minus x sub 0. Now what? Add it over. And what we get is this expression. X sub 0 minus f of x sub 0 divided by f prime of x sub 0 is equal to x. So we will call that our new guess, x sub 1. Watch how quickly I can make this work. Our first guess in this problem was 3. Our second guess will be 7/3. So all I do is 7/3 minus, let's figure out what f of 7/3 is. F of, where do I plug 7/3 into? So I take 7 divided by 3 and I square it, and I minus 5. I get 0.44. Divided by, it says f prime of x sub 0. So f prime was 2x. So I take 2 times, so 14 over 3. And I get 4.6 repeated. I don't know. I did 2 times because our derivative was 2x. So watch what I get now. 7 divided by 3 minus 0.4 repeating divided by 4.6 repeating. And if we do that, we get 2.238. Well, maybe that's closer to the actual answer. Watch what happens if I square that. Can you say impressive? Nobody thinks it's impressive. I mean, come on, look. What? All right. Okay, so fine. I see the point here, but I think 2.238 is a very good representation. And I want you to understand this as well, folks, that if you just look at the beginning here, you understand the mathematics of what was done, right? They pick a point, use it to find a point, draw a tangent line, look for the x-intercept. That's all it is. I mean, that's a pretty simple idea, yet Newton created his method that he would use to, approximate these things and find x-intercepts as well. Yeah. Yeah, that's all you use. And I'll even allow you to use your calculator. Obviously, would he have used a calculator? No. So, it would take a while to square 7/3, and, I guess you get, 49/9, but we all know how much you guys love fractions. So he was actually able to represent all these as rational numbers, which is cool. So you could come up with the best rational number to express the square root of 5. And, that's pretty cool. So, what do you think? Let's try an example. Flip it over. I was bragging about my chocolate chip muffins at lunch. That's Newton's method. What I find, I gotta pause it. What I find amazing right now is that it's frustrating. Okay, use Newton's method to approximate the following to 4 decimal places. So now I'm going to show you how we get it right to 4 decimal places, and we're going to do it rather quick. First of all, we need a function. If I want to approximate the square root of 7, I have to use f of x is x squared minus 7. I also need f prime of x, which is 2x. And I need an initial guess. Square root of 7? Sure, we'll use 3. So 3 minus f of 3, which is 2. How'd you get that? 3 squared is 9, minus 7 is 2. Everybody agree with that? 2 over 6. So 3 minus 1/3 is 2 2/3, or 8/3. Now, 8/3, if you were to square it, is not all that far off from the square root of 7, but it's not perfect. So again, you have think about this, a rational number to express an irrational. We could come up, so every time you do this, you could come up with a rational number. We're going to write them as decimals. And so because we're going to write them as decimals, it says to 4 decimal places, I'm going to write out 2.6667. Okay? 4 decimal places. Now, we know we're done when we do the number and all the decimal places are simply just repeated. We're like, okay, so we're closer and we're still getting those same decimal points, so we're done. So my new guess is 2.6667. Okay. Minus, I'm going to plug 2.6667 in. And like I said, Newton would not use a calculator here, but you guys can. 2.6667 squared minus 7. 0.1113 divided by 2.6667 times 2. I get 5.3334. And again, we want that number on top to be as small as possible. That's how far you are away from the x-axis. So you can see it's getting much smaller. And so if I do that, 2.6667 minus 0.1113 divided by 5.3334. And I get 2.6458. So that wasn't that much work, was it? If you square that, is that pretty close to 7? I mean, so, but do we know that the 2 is good? Do we know that the 6 is good? Do we know if the 4 is good? It would seem like it, but we don't know for sure yet. We gotta do it again and see that the 4 are repeated. Yeah. I'll show you right here. 2.6458 minus, now when we plug in 2.6458, 2.6458 squared minus 7. What is that? Yeah, that's times 10 to the negative 4th. So that's 0.00025 764, whatever. Divided by, let's see, 2.6458 times 2 is 5.2916. So if I do that, 2.6458 minus 0.1232564 divided by 5.2916, and I get 2.6457. The 5 rounds it up to 8. So we did get what we had before. And obviously, if you've gone this far, then you would say, gosh, I could probably write out a couple more and I'd be good. If you square this, I mean, come on. I mean, that's pretty ridiculously close, right? You stop when it repeats itself for all 4 decimal places. Yeah, you could end up doing 100 times. Right. Because of the slope of the curve. So, x squared, as we would change that slope, if you had, instead of x squared, if you had x to like the 1/16th power, that would be different. X to the 50th would almost be straight up and down. And you would just have to do it more often. You just have to continually work through it. So your assignment, all I want you to do, if you want to see Miss Amber, if you don't, that's fine. I just want you to do these 3 to 4 decimal places. That's it. it yeah, that's the cubed root. So that's it. How's that? So we could spend another good 2 days on Newton's method because there's a lot of really cool applications, but it you really don't do much with it. If we had an unlimited time, I would do that, but this is basically all we're going to do with it. We are going to talk about good and bad guesses tomorrow very quickly, and I will be getting you your study guides. So, bye, YouTube. Hopefully, you love Newton's method as much as we do, and hopefully, you love Amber Lob as much as we do. Goodbye. Right on.